Today, I'll cover my journey of taking this project from the original breadboard test version to its final version by creating my first custom PCB. I'll cover a bit of the design and ordering process, including the cost, review the quality of the PCBs, and then show the assembly involved, along with a lot of lessons I learned along the way and things I might do differently the next time. Hi, and welcome to Resin Chem Tech. Today I'm going to cover my personal journey in the process of creating my own first custom PCB. In the process, I'm going to go from this to create the final project. Now, I do want to give a special shout out here to Calfeet1 and Dorfmeister for both their assistance and encouragement as I muddle my way through this process. As always, be sure to check out the video description where there'll be links to a written guide, the parts that I used, and a GitHub repo which will have the design files for the PCB, the STL design files for the 3D printed parts that I used, and the code for the clock controller itself. In a previous video, I explored the use of I/O port expanders for ESP boards, and as an example of how those could be used, I built an analog LED clock. Now, as I stated in that video, this is not necessarily the best or most efficient way to make a clock. But when it was complete, I kind of liked some of the features I had coded into it and really just kind of wanted to keep it. But it was completely impractical to keep it in this form. Plus, I needed my breadboard and all those DuPont jumpers back for future projects. This is what finally encouraged me to try creating a PCB. And I should state this is not going to be a step-by-step guide on how to create a PCB. I'm going to show an overview and the major steps that I use to create mine, but if you are interested in a step-by-step guide, maybe even a live stream where I go from a breadboard all the way to ordering the PCB, let me know down in the video comments. Also note that this was my first time of creating a PCB, and I've already learned alternate ways and more efficient ways of doing some of the things that I did in this first design, and I'll talk a little bit about some of those at the end. Also note that I'm using Easy EDA as my design software, and so if you're using different software, the steps will probably be similar, but might be slightly different. With all that said, let's get into the overall steps of designing the PCB. So the first step is to create a schematic. With this schematic, what we're going to do is we're going to drop on all the components that are part of our design. And you'll find just about everything that you need in this library by doing a simple search. So here I will search for my MP23017 port expander, and you see I've got a number of different options. In fact, the biggest problem is sometimes going to be there are so many options is finding the right one. But it does give you a little diagram over here of what it looks like. So that's what I want. We're going to choose place. I've got 5 of these, so I'm just going to drop 5 of them here on my schematic, just in any particular place. And then we will go back and let's add the D1 Mini. Add the ESP8266 to keep it separate from the ESP32. Place one of those on the board. And we would continue to do that with all of our components. Once we've got all the components on there, then what we need to do is we need to wire the pins together. Now, this is not going to be the same as the PCB. We're just showing the connections in here. So for example, I can take my wiring tool up here. Let me zoom in. And I can take my 3.3 volts here from my D1 Mini. I can come over here and join it to my 3.3 volts on this. I have a lot of other 3.3 volts and a lot of ground connections. So there's actually a better way to do this. Using the wiring tool is fine for simple diagrams, but a better option is really to use what are called net ports. And so I can take a net port out here, and I can give this a name. So I'll just call this one 3V3. Once I have that net port, I can take this and I can copy and paste it to any place else where I'm going to need 3.3 volt. Then I can just join this to what's called the net port on each one. And that in the schematic says that all of these pins need to be joined together. That's going to be a little bit cleaner and easier to follow for more complex schematics. So you continue to do that until you get your final schematic with all of your components. This is the final schematic for my clock PCB. And you can see where I've made use of these net ports. This is really handy because I have a ton of ground connections. Every LED needs to be connected to the ground. Every port expander is connected to ground. The D1 Mini, basically everything here is connected to ground at some point. By using these net ports, When I get to the PCB, I'll have a ground plane, and all those will just automatically be connected to that ground plane, and I won't have to develop traces for them. Similarly, I have 3.3 volts. I have my I2C data and clock lines. I have those repeated a lot. Once all the components are there and labeled, do note that you need to account for every pin on every device. If you have a situation like this, like my D1 Mini, where I'm not using a lot of pins, you do need to come up here and place a no connect flag onto those pins. That's going to let the PCB know to go ahead and create a mounting pad or a through hole for that, but it's not really going to be connected to anything. Once all that's done, we're simply going to come up here to design, and we're going to convert this schematic over to a starting PCB design. And you're initially going to get something that looks like this. Although your board by default will probably be rectangular and will be just as big as the program thinks it needs to fit all the components, but of course you can change that. I've made mine here into a circle, and the nice thing is I can precisely control the dimensions of this. So I have a diameter here of 220 millimeters. This is where you're going to start placing all of your components that are down here. Now, by default, your board is going to have two layers, a top and a bottom layer where you can route wires. Now, you can add additional layers, which is what I ended up having to do here. But in my case, I have so many ground connections, I'm going to make the entire bottom layer a ground plane so that all my ground connections will connect to this bottom layer. Here you can see I've created this ground plane, and notice that it has a net of GND, which is the same net port that I use for all of my ground connections here. That means when I drop my components onto there, they will automatically connect to this bottom ground plane, and I won't have to create a trace for them. Now I can go back to my top layer and simply start dragging and placing my components in the approximate location on the board. Now notice these lines. This is showing all of the physical connections. They are not the traces. These are called rat lines, and they just show you all of the traces or connections that you're going to need to make. So at this point, it's really just a matter of dragging components around, putting them in approximate locations on the board where you think they're going to go. Once you have all those done, then it's time to start actually creating the traces in the PCB where these connections are made. So fast forward a few hours, and this is the final design for my PCB for my clock. Now, while it might look confusing, there actually are a lot of tools built into this to help you as you work along. In fact, there's even some auto routing tools. Sometimes those work, sometimes they don't, depending on the complexity. I actually did all this by hand, just partially because I was learning, and I kind of find it challenging to figure out how to route all of these wires so that they don't cross anywhere. But just as an example of how it will help you out, if I try to take a connection here and I try to run it across another wire, well, you can't do that. So it's not going to let me. In the case of running wires across other wires, that's where you have to use multiple layers. So I have a layer here where I'm running additional wiring where I can cross wires that are in another layer. Also note that there are tools, for example, all of my LEDs here, I didn't place all of those by hand. There was a tool that would put all of those in a circle, evenly spaced for me. And there's also something called a design rule check, which will let you know if you have any errors in your design rule. But even with all those design tools, I found it necessary to reorient some of my port expanders just to get the traces to work out. It's no big deal. It's just my LEDs are going to be in a slightly different order than they were on the original breadboard version, but that's easily fixable in the code. So it's really not as complicated as it looks once you learn to use the tool. Once your design is done and you have no design rule errors, you're ready to actually submit this to be made. Easy enough to do. We go to fabrication. We create what's called a Gerber file, and this will actually create a Gerber file that we can take and then upload to any PCB manufacturer to have our board made. On a manufacturer's website, I happen to use JLC PCB, but you can use PCBWay. Neither one of those are sponsors of this video, but again, you just need that Gerber file. And I actually uploaded it to a couple different sites and compared the cost. But all I have to do in this case is add that Gerber file that I just generated. I will select my Gerber file. It's going to read that Gerber file and be able to give me not only an estimated cost, but an estimated build and delivery time. It tells 4 layers. It has all of my dimensions. It read all of that from the Gerber file. There are some options down here. Let's say I want to have a purple PCB or a red PCB instead of green. But most of these other settings, really, unless you've got special need, are fine just to accept the defaults. That's pretty much what I did. I just accepted the defaults on these, Few things that I learned that I would change if I were to do it again, but there always is a minimum order, in this case of 5, I believe. And so you can see my total cost here is $44, so a little less than $9 a piece. And this is a little bit more expensive because I have 4 layers and just due to the size of the board. Most boards are only going to cost you anywhere from $2 to $3 a piece. So I did go ahead and I placed this order. It does their own internal check, but I got word back within, really it was just a matter of minutes that my boards had passed all the internal checks. I was able to enter in my payment information and my order was placed. One thing I kind of like about the JLC PCB site, and maybe other sites do this is the only place I've ordered from, you can actually follow the actual manufacturing of your PCB as it moves through the production process. So here's my first PCB, and I'm a little anxious to take a look. These did arrive in about 1 week. I placed the order on a Saturday, and they arrived from Hong Kong to my home here in Indiana on the following Saturday. Really took just a week, which to me is actually kind of phenomenal. We will open these up. They are wrapped nice. They are vacuum sealed inside of this. Get those loose. So we take a little closer look at this. All the silk screen looks very nice. Everything is actually quite readable. I'm a little surprised at how well it does look. And again, a little silk screen here on the back, which looks fine. Now the only question will be is, did I get all the circuitry right? But it does look like it was created exactly the way that I wanted. All of my port expanders here, my D1 mini in the middle, my buck converter here, of course all of my resistors, and of course all of the LEDs, and my 3 buttons here at the top. Of course I do now have 5 of them as well, but they actually look kind of cool, so I may find other uses for them even if I'm not going to build a clock out of these spares. Done some spot checking with the multimeter, and as expected, everything looks fine. Everything's connected the way it should be. And I've just tried to do some test fitting of some parts here. Nothing is soldered yet. I just wanted to see how everything was going to fit. And so far, everything looks good. But I have discovered a few things along the way that I will take into account should I ever decide to create another PCB. For one thing, I've opted to socket all of my port expanders into here. And the reason I want to do that is if a port expander goes bad or burns out, it'll be a lot easier to pop it out and replace it out of these sockets than to try to actually desolder it from the PCB. But in the process of doing that, what I did discover was the fact that when I put these in place, I'm covering up my I2C address, which isn't a big deal because I have each of these already labeled with the hex address. But more importantly, what I'm covering up is the little pin 1 indicator right here. And they are oriented differently with the different chips, so it's important to make sure I know which one is pin 1. So I've come through the little silver marker and I've made a mark outside of the footprint of this so that I can see that. But that'd be something for me for future reference to know that, if I'm going to make any kind of critical markings, I might want to make them outside of where the component's actually going to sit so I can see them after the component's in place. I'm probably going to go ahead and socket the D1 Mini here as well, partially for the same reason that if something were to go wrong, I could replace it. But more importantly, if I decide down the road that either the ESP8266 isn't quite handling the workload, or I want to do something like add Bluetooth, I will easily be able to come in here and swap in an ESP32 Mini. Since these white labeled pins are the same as the D1 Mini, and your 3.35 volts and ground are in the same spot, I could easily swap that out and just need to change a few GPIO numbers in my code. But that gives me the flexibility of replacing the ESP8266 with an ESP32 down the road should I need to do that. Now I will have to put this onto standoffs here, this PCB, because if you take a look at my original breadboard version, now I will be 3D printing a new faceplate. So this is the original wood one from the breadboard. But you can see I've got my ILI 9341 display here that has its own PCB and its own ESP32. And it does stick up quite a bit. So the idea is that this will mount over the top of that. This will eventually be powered off of the 2 pins here as well. So that means that my LEDs are going to need to be installed here on the back side of PCB. So I've got to figure out a way to make sure when I install these LEDs through these holes that the distance is the same for every one, so they are consistent in how far they are extending from this. And then again, finding a way that when I go to place this on top of the faceplate, how I'm going to get all 72 of those LEDs to line up and insert into the holes in the faceplate. But first things first, I'm going to go ahead and solder all of my resistors and all of my components except the LEDs onto the PCB. I've now completed what amounts to 235 of the 379 solder points, and yes, I counted. So the only thing left to go are the 72 LEDs with 2 solder points each. But a quick rundown, our 5 volts in. This is our 5 volt to 3.3 step down buck converter that's going to power the port expanders, and from there, the LEDs. Each of these 4 in the center will have 15 LEDs each for the minutes, and this one at the top will have 12 LEDs for the hours. Plus, it's also going to manage these 3 push buttons. Here is our 5 volt output to power the ILI 9341 display. And I did socket these, and I did go ahead and socket for the D1 Mini here. So it just plugs in if I need to replace it. But as I mentioned before, it does also allow the use of an ESP32. So if I decide I want to use an ESP32, again, all I've got to do is change a few GPIO pins in the code. So next up is to 3D print the faceplate and figure out how I'm going to install those LEDs. And as I mentioned, I will be using a 3D printed faceplate instead of the original wooden version that I used with the breadboard design. Part of the reason for that is I do need to get the holes in the faceplate precisely lined up with the through holes on the PCB for those LEDs, and I just didn't feel like I could do that with hand-drilled holes in a wooden faceplate. But by knowing the exact dimensions and layout on the PCB, and by using 3D design software, I can get those to precisely align. However, I couldn't do that with my normal design tool, which is Tinkercad, so it did involve me learning yet another new tool to create that 3D faceplate. Here is the design of that faceplate done in Fusion 360. It was my first time using Fusion 360 instead of the much simpler Tinkercad, but this design was a little bit too complex to do in Tinkercad. Now, one of the nice things is, since I had all of the dimensions for things like the LED spacing on the PCB, it did help in lining this out. And it's probably a little hard to see here, but each of these LED holes are countersunk, so each LED will insert exactly the same distance and leave just a small amount protruding on the top, which is what I wanted. Overall, I'm pretty happy with the design. The number cutouts are a little bit smaller than I would have really liked, but I couldn't really make it any bigger because this pretty much maxed out the print bed size of my 3D printer. And you can see that here was just laying down the first layer. My print bed size happens to be a maximum of 220 by 220, and the diameter of this clock is 215, so I only have 2.5 millimeters available on each side of this. The clock face itself is actually 5 millimeters thick, and it took about 11 hours to print. And this is the final printed version of the 3D faceplate. As you can see, I've went ahead and mounted the ILI 9341 in here, but overall it turned out pretty well. You can see a few lines here on the front. Now, if I really wanted to, I could sand that down and possibly paint that. But really, when it's compared, this is the original wood version, and this is a 3D printed version. I'm pretty happy with how it came out. And a quick spot check, kind of an alignment check. It does look like all of my holes line up perfectly with the holes in the PCB for mounting the LEDs. So now I have the standoffs glued into position. I did have to do a little bit of surgery here because it wanted to overlap these numbers or the LED holes, but the good news is it's now lined up and everything fits nicely. Now I did remove the ILI 9341 because I needed to run separate wires to it. Previously it was powered by the USB. I wanted to run separate wires to it because I'm actually going to power it off of pins here, off of my 5 volt that's coming in. While I waited for the glue to dry, I decided I would go ahead and work on the code for my ILI 9341. And again, I just want to show the date and the temperatures. These values are coming from Home Assistant sensors. This is an ESP home with a custom library developed by Dorfmeister. Dorfmeister is also the one that developed the PCB that this is mounted on. So a huge shout out to him, especially because a recent update of ESP Home actually broke the library, and within a matter of a couple of hours of me notifying him of that, he had a fix in place and a new version out. So this will go inside of the clock before the LEDs get installed. I made one final addition here to the faceplate before I try to assemble it together with the PCB, and that's adding these small blocks over each of the cutout numbers, and that's just to help block additional light from coming through there and kind of focusing the light from the LED. So the process is going to be, I've got to put all 72 LEDs here into the PCB, and then this will have to be lowered down and get all of those into these 72 holes. It's going to be a little bit of a challenge, but I'm just going to bend these slightly just to hold them in place until I can get everything seated into these holes. Remember, the top of the LED is actually going to protrude just a slight bit out of here. So what I've done temporarily is I've just put some rubber feet on there to hold this up off the surface, just so I can make sure the LED is seated all the way through. Not only do I have to be sure I'm getting the right color in the right hole for the design that I have planned, I also have to make sure I'm not reversing the polarity on any of these LEDs. Each LED has a positive and negative lead, and in my case, the negative always needs to go to the outside and the positive to the inside. Get one of those reversed, it's not going to work. Okay, just a quick shot here where I've inserted all 72 LEDs. They're really just held in place right now by a slight bend in this, so that should allow me a little bit of wiggle room to try to insert this now into the faceplate, get all 72 LEDs into the proper hole, at which point I can solder. Right, take another look here. This did take a little bit of time. I'm showing it from this angle because I can't flip this over because everything will fall out of the holes. But all of the LEDs are inserted into the holes and lined up. So at this point, all I need to do is kind of take these bins out, push them down a little bit to make sure that they're protruding through the front of the faceplate, and then I can begin the long, tedious process of soldering. I've completed the soldering of all of the 60 LEDs for the minutes. I've not done the hours yet, but I've decided I want to go ahead and give this the very first test before I do that. I generally like to test as I go along. It wasn't possible with this, and there are so many potential points of failure, from the PCB design to the 355 solder points at this point, or a myriad of other things that could potentially be wrong. But what I'm looking for in this test, when I plug it in, I'm hoping the ILI 9341 lights up, and we see the minute LEDs light up. Now, they're not going to light up in order, because if you remember, I talked about how I had to switch around the pin order from the breadboard version, and I'm still running the breadboard version code, but I at least want to see my LEDs light up on the minutes. Again, if they're out of order, that's fine. But of course, the biggest disaster would be if absolutely nothing happens. But I think it's important to make sure that I record and show my failures as well as my successes. So, big deep breath and crossing my fingers, and we're going to plug in our 5 volts. Okay, that's good. We got the ILI lighting up, and there goes our LEDs out of order, but they all lit up. So that is outstanding. The order is easy to fix. Oh, I even saw a few of my numbers light up just because they're hanging there and making contact. That is extremely promising and a huge sense of relief. Now I can go ahead and wire in my numbers and come back and we'll take a look at it again. All right, let's take a look at the final build version. If you look down here along the side, you can see where all of the LEDs are inserted in there. And here is the back side of that with the 3 push buttons at the top. And my power supply down here, which I'll be using a 5 volt, 5 amp power supply, which is more than enough for this. You could probably get away with a 3 amp, but it works pretty well, except there are a lot of things that I've learned. And next we're going to take a look at the features, and then I'm going to come back and talk about a few things that I think I'm going to change because I'm going to rebuild this PCB. So let me talk a little bit about the final features of the clock now that it's built, even though it's not really a matter of the PCB, it's more the matter of the programming of the clock controller. One thing is that these LEDs are simply too bright. I even have this setting at an angle, but when looking at it, it's just overwhelmingly bright. So I'm already planning on doing a version 2 of the PCB, which I'll be able to take the old one off and just attach a new one to the same faceplate. And I'm going to use much higher resistor values for these to dim those LEDs down a little bit. But by default, this is the display mode for the clock. It's going to light up the LEDs for each minute, and as you saw just a second ago, each time a new minute comes around, it redraws, or what I call sweeps, the LEDs. Now that is controllable through the push buttons, but what fun are push buttons when we can use MQTT and integrate it into Home Assistant? So I have control of all the different features and options through Home Assistant, and of course they can also be used in automations. So if I don't particularly like that sweep mode that redraws the LEDs each time, maybe that's a little bit annoying. As you can see, it just did right there. I can simply turn that sweep mode off. Now, when a minute rolls around, just the next LED will light up. In a similar manner, this little last blinking LED, that can be turned off or on as well. So I can leave that there. But because the LEDs are so bright right now, I decided that maybe I don't want all 60 LEDs to light up. So I do have the options of just showing a single LED, again, blinking or non-blinking for the current minute. Or I can up that to 5 LEDs, and these 5 LEDs will travel around the clock, or 10 or even 15 LEDs. So a number of different display options here that I can use. And I do have the option to turn off all LEDs, and I use that for the automation. The clock will continue to run. Right now, if I turn these off, in fact, I'll just go ahead and show it since it's an error. Turn all the LEDs off, which I do through automation at night, and I can turn all the LEDs back on. But right now I have a problem in my code that the hour LED did not turn back on. That's an easy fix, but it is something I'll have to fix. I also want to briefly talk about the IL9341 here. Even though it's a separate part from the PCB, it has its own PCB and its own controller, but since it is an ESP home, it's easy to use this for a lot of features. And since it's a touchscreen, I decided I would go ahead and make it so that when I tapped it, it would show me the 5-day weather forecast, and I can simply tap it and have it go back. Now, since it is integrated into Home Assistant and ESP Home, I can use this to show any information that I want. I can have it show alerts or messages or upcoming calendar events or anything like that that I wanted to on this clock. But that is separate from the PCB for the clock itself. And just a reminder, you can find the design files for the PCB, the clock face, and the code that I use for the clock controller all in the GitHub repo, which is linked down in the video description. And since I actually do have extra PCBs, it's going to make it fairly easy to make some changes to this to try to improve it. Again, for one thing, I am going to change the resistor values here. I'm going to go from 180 ohm to 2.2 kilo ohm, which is what I did on a breadboard test, to dim down those LEDs. Now, fortunately, I did make the decision to socket my port expanders and my D1 Mini, so I'll be able to just take those off of this board and move over to this board. The only thing I won't be able to move besides the LEDs and the resistors will be my buck converter and my barrel connector and my buttons. And the buttons are another sore spot, something that I would do differently if I were to design the whole PCB over again. For one thing, the place of this barrel connector, it's a little bit too low. Right now, I just have this in a little 3D printed stand, and it actually makes that angle hard enough that I'm having to use a little adapter to be able to plug that in. So I would move that up a little bit. And my goal at one point was to try to 3D print a way to actually hang this on the wall. But these buttons are going to be placed wrong for that. If I try to hang this on the wall, I'll no longer be able to use or reach these buttons. So I would change those. So while there are a number of things I might change if I were to design this PCB over again, I did learn a ton, especially the fact that it wasn't as difficult or as expensive as I first thought. In fact, I found it quite challenging and enjoyable. And I've learned even more since I created this first PCB, as I've already created additional boards that I'm going to use in future projects. So if you find yourself trying to use things like these electro cookie boards and either your circuit simply won't fit or you're creating the same thing over and over again, you might look into creating your own first PCB. And remember to check that video description for links to lots of more information, including a written guide to this project. As always, I would like to say thank you for watching, and I hope to see you soon.